the parallel circuit, current is going to divide. Is it okay to you people? But see, we have seen the formula. Again we are going to revise this. We have seen the formula, basically the current division for two elements connected in parallel. Yeah? If this is IS, this is R1, this is R2. Again I am recalling this for you people. See, the current I1 is going into the R1, the current I2 is going into R2. Now, according to the current division rule, the value of the I1 will be, the value of this I1 will be the source current multiply with opposite branch resistance. Who is the opposite of R1? R2. Opposite branch resistance divide by summation of resistances. R1 plus R2, simply. In the same way, we have the formula for I2 also. But see, observe, if you will clearly observe here, this formula is given for the two parallel connected elements. But here we are having 1, 2 and 3 parallel connected elements. Is it okay to you? And I4 is given to you people. Okay. And you have to calculate the different currents, I1, I2, I3 and I5. So how to find this? So we'll apply the simple current division formula. According to the formula, the value of I4 is source current. What is the source current? I1. I1 is the source current. Fine. Multiply with opposite branch resistance. Who is the opposite branch for this 3 ohm resistance branch? 5 and 6, they are the opposite branch resistance. But we need a single equivalent resistance here. I need R equivalent of remaining branch. Okay. And here, summation of resistances. Is it okay? So what is the R equivalent of the opposite branch resistance? Opposite branch, except these 3, 6 and 5, these are connected in parallel or not? They are parallel connected branches or not? Tell me. Starting point is same. Nothing is here. So this point A and this point, these 2 points are the same points. Okay. So 6 and 5 are connected in the parallel. So I1 is nothing but 6 connected parallel with 5 divided by R1. What is the R1? Plus 6 connected with 5. This is the equivalent of this 6 and 5. Is it okay to you people? Now come. What is the I4 given in the circuit? 4 ampere. I1 unknown. 6 and 5 connected in parallel combination. The resultant is 6 into 5 divided by 6 plus 5. Is it okay to you people? Here 3 plus 6. 6 into 5. 6 into 5 divided by 6 plus 5. Is it okay to you? Come here. This 4 equal to I1, okay, into 30 divided by 11. Here we take the LCM. It will be 33 plus 30 divided by 11. This 11 will cancel out this 11, and finally the I1 is, see here, 4 equal to 30 I1 divided by 33 plus 30, 63. Is it okay? So finally the I1 is nothing but 63 into 4 divided by 30. This is I1. Is it clear to you people? See, we have seen the formula for two parallel connected elements, but here we are having 3 elements. So suppose we are considering this branch, I am going to apply the current division formula for this branch. I4 is the current, and I4 is nothing but the source current. Source current is given I1 here, that's why I am taking I1. Multiply with opposite branch resistance. But we are having two opposite branches. Okay, that's why I am taking the R equivalent. I need the single resistance here to multiply with I1. So that's why I resolve these two branches. They are connected in parallel combination. So I resolve this 6 and 5. If they are connected in parallel, so combination is 6 into 5 divided by 11. 6 into 5 divided by 11. So I put the values in the formula and finally I get I1 is nothing but 63 into 4 divided by 30. We can further simplify this and it will be up to you. Okay. Now once you get the I1, can you identify it? Can you find out the I2? Yes, we can. See, I'll give you a hint for I2. I2 is nothing but source current. Now you already find out this I1. Multiply with opposite branch resistance. Except this, the opposite branch is 3 and 5. It means this is the parallel combination of 3 and 5. The parallel combination of 3 and 5. Divide by 6 plus R equivalent means 3 is connected parallel to 5. So finally I1 into, it will be 3 into 5 divided by 3 plus 5 divided by 6 plus 15 by 8. Simply directly I am taking 3 5 plus 15 and 3 plus 5 18. Okay. So finally I1 is, you already calculated I1, 63 divided by 60 or 30 and something. I1 is calculated already here. 3 into 5 15 divided by 8. Here you are taking LCM. So it's 48 plus 15 divided by 8. This 8 will cancel to this. And the I2. Here is the I2. I2 is nothing but I1 into 15 divided by 63. 48 plus 15. 63. This is the value of I2. Like this we can calculate the I5 also, I3 also, and I1 we already calculated. Is it clear to you people? Tell me. So now it's up to you to find out the values of I5 and I3. Can you do it? Good. Now we'll switch the topic. Now come to the very first topic, and that is practical voltage and current sources. Practical voltage source and practical current source. So before going to start the practical voltage, we will see what is the ideal voltage source. Okay. What is the ideal voltage source? See friends, the ideal voltage source, I'll take a white page for this. See, we are going to see the ideal voltage source. Okay. Friends, if you are having independent battery, having some voltage, take V. This is the battery you have. You are having two terminals of battery, A and B. Okay. Now it's depend on you that what you are going to do with this battery. You have to connect this in the circuit or taking some power from this or whatever. Okay. So what you are going to do, you are connecting one outer element to this battery, RL. This is the load resistance, that's why I am taking RL. So you will be having voltage VL across RL, is it? Because here the current will flow in the circuit. Because of this current you are getting VL across here. Now according to the ideal voltage source, the ideal definition of the ideal voltage source is the voltage drop across the resistance or load will be same, constant. Whatever current you will take out from the source, the voltage drop across the load will be constant. Is it not possible in practical? But for the ideal voltage source, if current value will increase the current value, there will be no change with VL. The VL will be same at all. VL is nothing but the source voltage. The source voltage is same. It will not drop. Whatever current you can take out of this circuit. or this source. Means the VI characteristics, if you will see, also here the x-axis is current I, this is the voltage. Now what I am saying, whatever current you will fetch, the value of VL will not change, and VL will be always VS, source voltage, like this. This is the ideal voltage source. They are saying whatever current will take out from the source, the voltage drop of the source will be constant. The voltage of the source will be constant. This is the ideal voltage source. But in practical, friends, this will not happen. If the value of current will be increasing, the value of the current will be increasing, the VL will drop. Like this. The VL will drop. Okay? Like this. Why? Because in practical, for any voltage source, we are having internal resistance also. This is the practical voltage source actually. Two terminal. But this source also having internal resistance of it. Internal resistance. We take it. This is the practical voltage source. Ideal voltage source is nothing, simply given by the terminal value Vs. There is no resistance here. Means Rs is 0 for the ideal. Is it okay to you people? See, for the ideal voltage source, the internal resistance is 0 or the source resistance is 0, but in practical it exists. Now if you will connect load resistance RL, so here VL is given like this. Now if you will take the current IL, whatever current you are taking, what will be the effect of that current over the VLC? Can I identify this VL? Yes, I can easily find out this by applying KVL. VNC, I is flowing in the circuit, so voltage drop will be here. That voltage drop will be R in multiply with I, simple Ohm's law. Now apply the KVL here. I can easily get the value of VL. V in is nothing but the delivered voltage is nothing but the consumed voltage. Consumed voltage is R in I plus VL. Like this. Is it okay to you people? See, this is simply we are moving from VN getting VN minus this and minus VL. It's over. Is it okay? So you are arranging delivered voltage is equal to the absorbed voltage. Now what is the value of VL actually? VL is nothing but VN minus R in I. Okay. R in fixed. This is the internal resistance. V in fixed, R in fixed. Now if current is going to increase, the voltage will automatically drop. See, the voltage will drop. This is the ideal and practical voltage sources. Is it clear to you people? Now if we consider the ideal current source and ideal voltage, practical voltage source, we'll see. Wait a minute. We have done the practical voltage sources. Now we see the practical current source actually. Yes. Wait a minute. Now see the current source. Ideal and practical. Current source. Is it okay? Now see, the current source we show by like this. This is nothing but the current source. Is it okay? I am giving the name IS. Come here. This is the terminal A and B. The same as the voltage source. This is the current source actually. Okay. Now you will connect load RL here. Okay. So because of the same current is flowing in the RL, you are having voltage drop across here VL. Is it okay? Now what is the definition of ideal current source first? Ideal current source is saying whatever voltage is assigned across the load, current will not change. Current will not change. Okay. Current will be constant. There in the ideal voltage source, the voltage was constant. Here the current will constant. Whatever value you change for RL, the IL will be same. Okay. If RL will be 10 ohm, RL will be 100 ohm, RL will be 1K, 2K, 10K, 100K, the value of the current will not change. The value of the current will be same at all time. In the ideal voltage source, the voltage was same, whatever current you are taking from the circuit. Here, whatever VL you take from the circuit, the value of input current will not change like this. Okay, means if you will draw the characteristics, they are saying whatever voltage you take, the value of current will be same always. See, and that is equivalent to IS, because IS is the current in the circuit. So this current will be same, whatever load, resistance or voltage we are taking, no matter. Like this, it will be a constant. You will increase the load voltage, no matter. Okay, like this. But in the practical, this is not possible, because the practical current source is given by one parallel resistance Rn. Actually, this is the practical current source. This entire thing is the practical current source. This is the practical current source. Okay. Right? And what is the practical voltage source? This is the practical voltage source. Means for the voltage source, the resistance will be connected in series with, and for the practical current source, the resistance, internal resistance will be connected in parallel with the value of current. Okay? Is it okay? Now we are going to connect the RL, means load resistance. In the load resistance, now this current will not go fully. Means current will drop now because of this internal resistance. Okay? Because some current will go here also. So for the ideal, there is a no R in. See, this is the ideal current source. Is there any resistance in between two terminals? No. This is the open circuit. Means R is infinity. Open circuit means infinity. Infinite resistance offering by two terminals or points. Okay. So for the ideal, okay, later we'll discuss. So for this, if we will talk about the VI characteristics, if you will increase the value of voltage here, so current, see, you are increasing the voltage. This voltage is same as for RL and Rin. You are increasing the value of VL, suppose. So the current going into this branch will be increasing. Is it okay? Because V is directly proportional to the I. If V is going to increase, the current will also increase. So this I will be decreased or not. So actually, this circuit will be like this. Is it okay? So this is the ideal practical current sources. Come to the transformations now. We are having two types of transformation: voltage to current transformation and current to voltage transformation. See, the current and voltage transformation will be beneficial sometime to solve the circuit. Actually, that's why we are going to discuss about this. This is the very easy concepts actually. See, transformation, right? Okay, two types of transformation we are having: voltage to current and current to voltage. Means we are given with one circuit and we have to convert the voltage circuit into the current circuit. This is nothing but the voltage source to current source transformation. And if we are having the current circuit, we will convert into the voltage circuit, and it will be a current to voltage transformation. Okay. So when we can transform the circuits, when we can transform the voltage source into current source, here is given the specific condition. See, what is the practical voltage source circuit? The value of the battery will be connected in series with input resistance of the source. This is the voltage source given here. Is it okay? I am taking R in, I am taking V in. Now the source transformation I am doing. I am doing the voltage transformation into current transformation. Okay. So what is the circuit for current? Always parallel connected resistance will be there with current source. Is it okay? See, this is the transformation. This is the simple transformation. This voltage transformed into current. This Rn is given here. The same Rn is here in the parallel with current I. But what is the value of this I? By Ohm's law, this I is nothing but V in by R. Simple. Like this. Okay. See, this is the circuit. The circuit is providing the current to the system, and that current is nothing but V in divided by R in here. So we can easily convert this. So we can easily convert this voltage into current form. This is nothing but the voltage to current conversion, and vice versa. If you are having this circuit, if you are having this type of circuit, you can convert into equivalent voltage. First write the voltage circuit. As you know, the series resistance will be connected with the voltage battery like this. So we will convert this, we will convert V, and this is R in. This is R in. The resistance will be same whatever resistance we have in the parallel combination, and this will be V. So what will be the value of this V? By the Ohm's law, V equal to the given parameters of I and Rin. So this V equal to the given parameters I into Rin. Is it okay to you people? It's a very easy concept actually, transformation, source transformation we call it. Okay, so I'm taking a simple example. See, check battery 5 volt, and this is nothing but 10 ohm gain. I'm taking a branch across A and B, and the value of branch is same, 10 ohm. Now I can convert this circuit into the current form. Okay, because this entire circuit given here, left of C, satisfied the voltage circuit. Practical voltage circuit is nothing but the value of voltage in series with the resistance. So up to this part, I can convert into equivalent current source, okay, or current circuit. But before convert to that, find out the current here. What is the current here? In the 10 ohm resistance, this current is 5 divided by 10 plus 10, 20. So 1 by 4, 0.25 ampere is flowing initially. Okay, now we are going to convert this. We are going to convert in equivalent resistance. Equivalent current source, current circuit. So if the current circuit is, the value of the current will be connected parallel with resistance. This is the point A and B. Across the point A and B, I am going to convert this voltage circuit into current circuit. This will be current. The resistance will be same as given in the, the value is 10 ohm. Okay. This is the AB. Here also the 10 ohm is connected. Is it okay? Now tell me the value of this current. The value of this current is V by R. Is it okay? What is V? V is 5. V is 5. What is R? R is this 10 only. Don't consider this 10 and then 20 because we are looking for this circuit from A and B. So 5 divided by 10 means 0.5. 0.5. So this value of this current is nothing but the 0.5 ampere. Is it clear? So I am removing all this. The value of this current would be 0.5 ampere. This will be 0.5 ampere. Is it okay? So we converted this circuit into the equivalent voltage circuit. Now observe this. Initially the current, suppose this is the load resistance. Across A and B, suppose 10 ohm is the load resistance. In the load resistance, the value of current is 0.25 in this circuit. Will it be same in this circuit or not? What we are saying, these two circuits are equivalent circuits. If these two circuits are equivalent circuits, so the value of currents will not change. Okay? Find out the current in this 10 ohm. Can we apply current division rule here? Yes, we can apply. So this I will be source current is 0.5. Multiply with opposite branch resistance. Tell me the opposite branch resistance. We are going to calculate I in 10 ohm. Opposite branch resistance given as 10 ohm. 10 ohm. Divide by summation of the resistances. 10 plus 10. 20. Cancel. So I is nothing but 0.25 ampere. See, in both cases the current is same. Okay. So that's why we are calling it, these are the equivalent transformation. Here, the circuit parameters are not going to change. If the current across the element in a voltage source circuit is something, the same current will be there in the current circuit. Okay. So these are the equivalent circuit. Fine. Come to the next one. Independent and dependent source. Okay, friends. As we have seen the voltage and current, two types of the circuit like this. In many problems we used this plus minus combination and we have given the name voltage source. And this arrow type of structure we have given the name current source. These are the independent sources of energy. What the meaning of independent source? Independent source means we can't change the value. Suppose this is the 5 voltage given here. So it will deliver 5 volt always. We can't go inside the source and can't change the value of 5 volt. We can regulate but can't control it. That's why it's uncontrolled device or independent source of energy. We can't control this value. If this is 5 ampere, so this will deliver 5 ampere in the circuit. We can't control this. So these are the independent source of energy. An independent voltage or current source is an idealized circuit component that fixes the voltage or current in a branch respectively to a specified value. The value is 5, so it will deliver 5 voltage only in the circuit. Okay. Or independent source, I can say the source who provides energy to the circuit is called the independent source of energy. He is providing the circuit by its own. Okay. Is it clear? It's very simple, independent. But come to the dependent source. What is the dependent source? I think in the last slide only we have seen the dependent source represented by the dependent source represented by this diamond type of structure. We are having terminal A and B. So this is the diamond structure and this is suppose voltage source. So this voltage source is nothing but the dependent voltage source. Dependent, okay. This diamond shape shows the dependency. Is it okay? Now we will discuss about the dependent source in brief. Come to the dependent source. Dependent source is the source whose value depends on the circuit parameters. What I am telling? In the dependent source, the value of the source will depend on the circuit parameters. See, consider a circuit. I am taking one simple circuit over here. The value of this is take 5 volt, this 2 ohm, 3 ohm, and value of this is 3 I0, where I0 is the current passing through 2 ohm resistance, like this. See, now this is the dependent current source. Why current source? Because arrow inside the diamond. That's why this is the current source. And the value of this current source, it depends on the I0. I0 is the circuit current flowing in the 2 ohm resistance. So see, the value of this source is dependent on the circuit parameters. So dependent sources are the source. The dependent sources are the source whose values depend on the circuit parameters. Is it okay to you people? Okay, fine. Now, so according to this, we are having 4 types of dependent sources. So we are having 4 types of sources. Let's see the dependent sources. See, the first source will be like this. The value of this is, suppose, kV0. Okay, so this source is the current source. Why current source? Because of this arrow inside the diamond. So this is definitely value of some current. Means like this. So this is the current source. Current source. This source is given is the current source. But the current depends on which value, which parameter of the circuit? Voltage, right? So this current is controlled by voltage or current? Tell me. Yes, absolutely. This I is controlled by voltage value. So this is the voltage controlled current source. This source you are seeing here is the dependent source. And which type of dependent source? Voltage control current source. Is it okay to you people? This is voltage control current source. Here this is the input. Here this is the output. So this is the input output topology. Input is voltage control, output is the current source. Now for the same circuit, same independent source, I am taking again. This is the current source only, clearly visible here, the current source only, and the value of this is nothing but kI0. Now see, this which type of source is this? Here, this is current source, and this current is controlled by which parameter of the circuit? Current or voltage? Current. This is current control current source. So this is type 1. This is second type of dependent source. Now come to the third type of dependent source. So like this, it's given a voltage source V, and the value of this voltage is nothing but kI0 source. Which type of source is this? Yes, voltage source. And the voltage is controlled by current, so this is the current control. CCVS, current control voltage source. And the fourth one and the last one is again the voltage source, and the value is kV0 source. So this is the voltage source, and the value of the voltage is dependent on voltage. So this is controlled by voltage. This is the voltage control voltage source. So here, these are the types of dependent sources, 4 types. Voltage control voltage source, voltage control current source, current control voltage source, current control current source. This is the current source. Okay, I'm having 4 types of dependence. Is it clear to you people? Good. Now come to the series and parallel connection of the resistance. It's very easy, and you people know already, I think. The series, we know about how to connect the elements in series. Okay, ending part of one resistance will be connected with the starting part of the another resistance, and there should be no obstacle over here, or no branch should be connected in between them. Then only we can say these are the series connected. In the parallel connection also, we have seen the resistances or elements will be connected in parallel if their starting points will be connected each other and ending point will be connected each other. So we know about the series and parallel combination. But when we will connect the different resistances into the series, then what will be the equivalent of the circuit? Simply I am telling you, if consider a series circuit where R1, R2 up to Rn are connected in series, the current will be same as we know. The voltage will be divided V1, V2, V3, because we already know that in the series circuit the voltage is the dividing factor, and in the parallel circuit the current is the dividing factor. Okay, so if I am having one series combination of some elements R1, R2, R3, R4, I am considering 4 elements, they are connected in series. So the current will flow in the circuit is I. Equivalent of this will be given by the summation of all this, means R1 plus R2 plus R3 plus R4, like this. Is it okay? So when the resistances are connected in series combination, the equivalent resistance of the circuit will be the summation of all given elements or all given resistances. Is it clear to you? Good. Now come to the parallel combination. In the parallel combination, this is the parallel combination. In the parallel combination, the R equivalent is given by this. 1 by R equivalent is nothing but 1 by R1 plus 1 by R2 plus 1 by R3 and so on. Okay. Is it clear to you people? This is the formula for parallel combination. So if you are having only two R1 and R2, two elements are connected in parallel, so the combination will be R equivalent equal to 1 by R1 plus 1 by R2. So if you will solve this, R equivalent equal to LCM, take LCM R1, R2, R1 plus R2, now it will be inverse and your R equivalent will be R1, R2, R1 plus R2. So for two circuits or two elements connected in parallel, directly we will use this formula R1, R2 upon R1 plus R2. And this is the original formula, 1 by R1, 1 by R2. Here the impedance, this is the summation of impedances, this is the summation of the admittances. Is it okay to you people? So it is a simple, that's why we are not going in deep, we are not deriving it, how it's come, how this formula is coming here. Okay. See the problem here. They are asking find out the R equivalent of the circuit. Can you find out the, I told you to find the R equivalent, start from the last portion of the circuit or ending portion of the circuit. See, 1 and 5, these two resistors are connected in series. So the combination of these two is 6. Is it okay? Why am I adding this? Because we know we can add. So the resultant will be 6. Is it okay? And it will become one branch. Now this 6 and 2, these two are connected in parallel? No. Why? Because starting point is same, okay, no problem. But ending point is not same. This is the ending point of 6 and this is the ending point of 2. If these two are connected to each other, then only we can say these two are connected in the parallel combination. Else these are not connected in parallel and they are not connected in series also. What about this 6 and 3? Yeah, they are connected in parallel because this is the starting point, this is the ending point. Okay, so we can merge them, these two. If 6 and 3 are connected in parallel, so equivalent will be 6 into 3 divided by 6 plus 3 as we see in the formula. So 6 into 3 divided by 9. 3 3s are 9, 3 2s are 6. So the combination is 2. So I am drawing here the final combination. 2 is already given. The combination of these two, 6 and 3 become 2 again. Here the 6 ohm branch is connected like this. Here the 4 ohm is connected, and this is the terminal across which we have to calculate the R equivalent. Okay. Now again we can resolve this. This 2 and 2 they are connected in series combination. So 2 plus 2, the resultant will become 4. So wait a minute, I'll erase this. I'll take a resultant. This is the resultant, and resultant value is 4 ohm. Is it okay? Now this 4 and this 6 are connected in again parallel combination. So the resultant of this 2 is 4 into 6 divided by 4 plus 6. Is it okay? It means 6 into 4 divided by 10. 2 2s are 2 5s are 6 2s are 12 by 5. The resultant combination of these two is 12 by 5. So your final combination is 4 in series with 12 by 5. Is it okay? So what is the final R equivalent? R equivalent is nothing but 4 plus 12 by 5. 4 plus 12 by 5. This is nothing but R equivalent. Is it okay? This is the way to solve the circuit for R equivalent. And this is for you, homework. Okay? Come now, this is also the very important transformations, star to delta and delta to star. Friends, sometime when we resolve the circuit by series and parallel combination and we want to get the R equivalent of the circuit, sometime we encountered with such type of circuit in which there is no series combination, no parallel combination. And we know to solve for the series and parallel combination only. Okay. So sometimes we encountered, see in this bridge circuit, R3, R6, R4, R5, R2, R1. If you will look over this bridge, you will feel that no resistive element is connected in series or parallel combination. See, you can see this R3 is not connected in series with R4 or parallel with R4, this R3, R6. There is no such combinations, neither series nor parallel combination. So how can we solve the circuit? If someone will ask that find out the R equivalent of this circuit across the terminal A and B, what we will do? Nothing, because no one is connected. See here, R3, R4, R6, no one is connected in the parallel or series combination. So that's why this star connection and delta connections are coming into the pictures. Okay. So before going to discuss the formula for star and delta connection, we see the structure of delta and star. If three resistances are connected in this way, so this is the star connection. It's making a star, that's why we are calling it the star connection. This is looking like a Y connection also, so this is the Y connection. And sometimes when you will stretch the 1 and 3, it will become a T, alphabet T, so we are calling it the T connections also. So this is the structure, one common point for all and three different points. So I can convert this star into delta. So we should understand the delta structure also. Delta of pi. If three resistances are connected in this way, RC, RA and RB, three different points, so we call it in delta connection. They are in delta connection. They are in delta connection. We call it the pi also, because if I'll stretch this, it will become pi. Okay. So if we are having star to delta, if we are having star connection, we can convert into delta, and if we are having delta, we can convert into star. See the formula for that. I am taking a star connection first. This is the common point for all, like this. Three points you have. You are having 3 points. Okay. And the value of resistances are R1, R2 and R3. Your task is to convert it or transform it into equivalent delta, and we have seen this is the delta, this is the delta, and this is star. Okay, so we are having a star. Now we are going to convert this star into equivalent delta. So I am going to construct this here only. Okay, 3 points A, B and C. Here the value of this resistance is RA, RB, RC. In the star we are having 3 branches. Here also we are having 3 branches. Is it okay? Now come to the formula. What is the formula? Here also we are not going with the deep. We are not discussing about the derivation, how it comes. Directly we are seeing what is the formula for RA. What we are going to do, we are converting this star into equivalent delta. So this RA I will represent in the form of star elements, means in the form of R1, R2 and R3. This RA is nothing but, this transformation is nothing but star to delta, star to delta. Okay. So RA is nothing but, RA is connected with 2 branches, R1 and R2. So I'll add them, R1 plus R2. In the third term, I'll multiply both R1 and R2 and will divide by the remaining part, that is R3. Is it clear? It's very simple to remember also. What is RB? Now you people will tell me. Tell me RB. Where is the RB? Here. RB is connected with R3 and R2. Summation of R3, R2. In the third term, we have to multiply R2 and R3. R2, R3 I multiply, divide by the remaining resistance, R1. Is it okay? Come to the RC now. Where is the RC? Here is the RC. Connected with R1 and R3. Okay, no problem. R1, R3 plus R1, R3. The remaining one is R2. This is the star to delta conversion or star to delta transformations. Here, now I can remove this star and I am having only delta now. This is the equivalent. There is no change in the circuit parameters. If we are converting a star into delta, there is no change into the circuit parameters. Is it okay? That's why this RA is nothing but in the form of the star parameters. Is it okay? Or any problem you have? Okay. Now come to the delta to star. Okay. Now we'll see delta to star. Now I'm having a delta circuit. This is the delta circuit. Points A, B and C. Here this one is the RA, this RB, this RC. And my task is to convert this delta combination into star. Okay. So, wait a minute. Star. This is a star. This value is R1, this value is R2, and this value is R3. Now, if you want to convert the delta into equivalent star, you should have the values of star parameters in the form of delta parameters. Means you need to calculate now the value of R1. So R1 should be in the form of delta parameters. So R1 is here. R1 is connected with RC and RA directly. So this is RC RA divided by summation of RA RB RC. RA plus RB plus RC. Very simple. See this. RC RA plus RA plus RB plus RC. Is it okay? Come to the R2. Come to the R2. This R2 is connected with RA and RB with a dot. So I'll give a dot here like this. It's technique to remember, okay? And the RA plus RB plus RC. Simple. Come to the R3 now. R3, here is the R3. R3 is connected with RB and RC. So multiply RB and RC. In the denominator, summation of RA plus RB plus RC. Simple. This is delta to star conversion. Now your delta is converted into star. Now you can remove the delta from the circuit. Don't have delta now. You converted the delta connection into star. Is it okay? So this is delta to star and star to delta conversion or transformation. Is it okay to you people? Good. Now come here in the next slide. Here we are having some problems based on delta to star, star to delta conversion. Convert this is delta. This is delta, okay. Delta network in the figure to equivalent Y network. See, here they have given the delta and they are asking to convert into star. Okay, they have given the values also. 25 ohm. Here it is, tell me, 10 ohm, okay, correct. And here it is 15 ohm, okay. 3 terminals, C, B and A, right? Now, our task is to convert this circuit in equivalent star. The term I am saying equivalent star means the value is not changed. Okay. The circuitry is changed, but effect of this conversion into the circuit is 0. Okay. So this is star. Okay, fine. Suppose this is R1. Take this R2. Take this R3. The value of R1 is 25 into 15. Correct? Remember the formula. If you want to get the R1, we'll multiply this to 25 and 15 and summation of all. Means 25 plus 15 plus 10. Is it okay? So at the end, you are getting 25 into 15 divided by 25, 30, 40, 50. This one is the 50. Finally, you are having 7.5. Is it correct? Yes. Absolutely correct. So this R1 is equivalent of this circuit 7.5. The point is same, B. This point will be connected with C, and this point will be connected with A. Okay. What about this point R2? R1 is over. Come to the R2 now. R2 is nothing but R2 is connected. R3. It is R3. R3 is connected with 10 into 25. So 10 into 25 divided by summation. It is 50. So it's become 5. Correct? So here in this branch we'll mention 5. This is 7.5. Come here. 10 into 15 divided by 50. Okay. So it's 5 and 3 times. So this is 3 ohm. This is equivalent circuit of this. Now here in the next question they're asking, obtain the equivalent resistance for the circuit and use it to find the current. You have to find this current and you have to find this R equivalent also. R equivalent across A and B. So I'll say RAB. Okay. The appearance of resistance across A and B is nothing but the equivalent resistance. Is it okay? So this is homework to you people. So friends, it brings me to the end of this lesson. In next video lecture, we'll directly switch to the practice session and we'll solve gate problems and some books problems. We'll meet in the next video lecture. Till then, take care and bye.